Good morning, students. So in this session we'll discuss about the inverse Z transform. Okay, the last two session we'll discuss about the Z transform. So in this session inverse Z transform, because we need to transfer the signal in a Z domain, and after that again we should get it back in time domain. So for that the inverse Z transform is used. Okay, using inverse Z transform we can convert the signal from Z domain to time domain. Okay, so that you can do by partial fraction method, power series method, different methods are, we will see the partial fraction method. So before that the system function, so you know that the system function of the LTI system, function of an LTI system. So this is a LTI system. So x of n, this is y of n. So y of n is equal to a of n is equal to the summation of k equal to minus ft plus ft x of k into h of n minus k. So by taking z, that is a convolution, x of n convol of h of n, take z transform of this function, which is equal to z transform of this one, you will get x of z into h of z z. So the y of z by x of z, which is equal to h of z. So the h of z is a system function. Okay, so which is the h of z is the system function of the unit sample response of the system h of n. So system function, which is the z transform of the unit impulse as a unit sample response of the h of n of the system. So in system function you take z transform of this equation. Normally the difference equation you can consider the system described by the difference equation y of n is equal to minus summation of k equal to 1 to n a k y of n minus k plus the summation of k equal to 0 to m b k into this x of n minus k, b k into x of n minus k. So take z transform for this equation, take z transform. So y of z is equal to k minus the summation of k equal to 1 to n a k into z minus k into y of z plus summation of k equal to 0 to m is b k into x of z into z minus k. So y of z, you can this term can bring in left hand side 1 plus summation of k equal to 1 to n, this is a k into z minus k is equal to summation of k equal to 0 to m b k into z minus k, okay, into x of z. So y of z by x of z, which is equal to h of z. So it is equal to the transfer function, the summation of k equal to 0 to m bk into z minus k divided by 1 plus summation of k equal to 1 to n ak into z minus k is a system function. So this h of z system function is a rational function. It's a rational. So in terms of the stability of the system, okay, so the condition for stability of the causal LTE system, the causality and stability, okay, for any LTE system. So the h of n equal to 0 for n is less than 0. This is a causality. For n is less than 0, this is a causality function. Stability, the ROC of the system will be exterior to the circle having radius less than infinite, okay, when the system is causal. So for stability, the summation of n equal to minus infinity to plus infinity, h of n will be less than infinity. This is for stability. This is for stability. Okay. So inverse Z transform will take some examples, and normally the y of z, you know that y of z by x of z, you can expand this equation, okay. So this is h of z system function, okay. So I will take some example for inverse Z transform. So before that, the ROC, okay, and how to find the system if it is defined by a per n v of n. We have derived if the system contains more than one poles, then the ROC will be how to determine. So we will take one problem. So x of z, for example, 1 by 1 minus 1 by 2 z inverse plus 1 by 1 minus 2 z inverse plus 1 by 1 minus 5 z inverse. Take this example. So what are the poles? Okay, the poles at z is equal to 1 by 2 and z equal to 2, this one and 5. Okay, now how do you define ROC? Okay, ROC, just for this poles, how to define ROC, and the system, how you can classify the system may be a okay stable system and causal system, or it may be a stable and non-causal system, or it may be a unstable system and causal, or unstable and non-causal. You can classify the system either it is a stable system or unstable system. It is a stable and a causal system or stable and non-causal system. For example, if the system defined by the node, the systems defined by a power n, u of n, when it will be causal in the region outside the circle. Outside the circle will be causal in the region outside the circle of radius a. For example, if the system contains more than one pole, so here how many poles? 3 poles. There are 3 poles, P1, this is P2, this is P3, for example. P1, P2, P3. The system has 3 poles. Then the ROC will be multiple poles. Then the ROC will be, so what are the poles? P1, P1 is, what is the P1? 1 by 3, 1 by, that is a 2 and 5. Okay. So the 3 poles are P1 is equal to 1 by 2, P2 equal to 2 and P3 is equal to 5. If the system has more than one pole, then the ROC will be the region outside. ROC will be the region outside the circle, with the largest pole as its radius. And the system will be causal, so radius, and the system is causal, okay, in the region outside the circle only, So the system is denoted by a power n, u of n, so will be non-causal, inside the circle, of radius a. Similarly, the system contains more than one pole, then when it will be non-causal, which area is a non-causal? So if the system has multiple poles, then it will be completely non-causal, multiple poles only, So the system will be non-causal only inside the circle, only inside the circle with the smallest pole, as its radius, smallest pole. So now if the system is defined by a power n, u of n is stable only when the system will be stable, stability of the system is stable only if the ROC contains unit circle, contains the unit circle, If the ROC contains a unit circle, then it is stable system. Okay. If the ROC is inside the unit circle, it will be unstable. So from these arguments we can classify into the system may be stable and causal, or stable non-causal, unstable and causal, unstable and non-causal. So if the system has multiple poles, so the system will be causal only region outside the circle of radius A, so outside the circle with the largest pole. Okay, that is a causal region. So it will be non-causal only inside the circle of radius A if it has multiple poles, which is the lowest, smallest pole as its radius. So in the system the largest one is a 5, the smallest pole is a 1/2. So it will be causal only outside the circle with the largest pole. So in this example, you conclude that whether the given system is stable or not for the above problem. So the 3 poles are 1/2, 2, 5. So what is the ROC? Now ROC is equal to, will be the area outside the circle with the largest pole as radius, its radius. This is z equal to 5. So the system is causal. System is causal only outside the circle, System is the smallest. What is the smallest pole? Is that equal to 1/2? No, the smallest pole. So the system is non-causal. Inside the circle of radius. Inside the circle of radius equal to 1/2. So this, since this ROC, so what is ROC? Outside. Since the ROC does not contain the unit circle does not contain the unit circle, the system is unstable system. Okay, stability poles determination of. So this is now the system is unstable system. So this system is unstable system. So if the system has multiple poles, the ROC will be the outside the circle with radius largest pole. Similarly, the non-causal will be inside the circle of radius z equal to 1 by 2. So this is a non-causal. Since the ROC does not contain the unit circle, you can say the system is unstable. Okay, these are the conditions you have to check whether the given system is stable or not. How you can draw this one? See, okay. For example, r is equal to 1 will take. So this is r equal to 1. ROC, this is unstable. So this ROC, so this is stable and causal region. Causal region. So this is your unstable non-causal. Unstable non-causal, this is stable and okay. This is a U of n. What is U of n? So ROC of U of n. This is ROC of U of n. ROC of A per n U of n. Okay. ROC of A power n U of n means same. This R less than A. So this is a non-causal region. This is your causal region. ROC is a causal. Okay. So now normally for right side sequence, the ROC will be the properties. If you see, the ROC does not contain any pole. ROC does not contain any poles. Okay. If x of n is a finite sequence, if x of n is a finite sequence, for example, finite sequence, then the ROC will be the entire z plane except z equals to 0 and z equal to infinity. If x of is a finite sequence, the ROC will be the entire z plane. The ROC is entire z plane except z equals 0 and z equal to infinity. So normally The ROC for the right side sequence is ROC for the right side sequence. So that is outside the circle. ROC, this is for right side sequence. For left side sequence, the ROC will be inside the, for left side sequence, the ROC will be the inside the unit circle. This is for left side sequence. For both side sequence, the ROC will be, for both side sequence, generally the ROC will be this is a ROC for the both side sequence. ROC for both sided sequences. Both sided sequences. So you can take some example. X of n is equal to a power n u of n plus b power n u of minus n minus 1. So z is greater than a, and here the z is less than b. So z is greater than a, this is a, okay. The other one is z is this is b. The ROC will be this is the ROC. This is the ROC. If in case if b is greater than a, this is, if b is less than a, then it will be, if b is less than a, then it will be so this is your b, this is your this is your a. This ROC will be now for this one, for this one. These are the properties of, some of the properties of Z transform. So you can refer the prescribed textbook. So now we will discuss about the inverse Z transform. Okay. So I think we will take some problems for inverse Z transform. Okay. Okay. We will take some of the problems for inverse Z transform. Okay. So we'll take x of z is equal to 3z squared plus 2z plus 1 divided by z squared plus 4z plus 3. So now 2 plus will solve. Second one, you take, find the inverse the transform of x of z is equal to 1 divided by 1 minus 1.8 z inverse plus 0.8 z minus 2. For the following conditions of ROC, modulus of z is greater than 1. Okay, I think this problem from John Prokis. And first condition, and the second condition less than 0.8, and the third condition is greater than 0.8 and less than 1. Then how to plot the poles and zeros. Okay, and h of z is equal to 7 minus 7.6 z inverse by 1 minus 2.4 z minus 1 plus 0.8 z minus 2. So, this is a system function. You have to specify the ROC of h of z and find the unit sample response h of n. So, if you want to find h of n, means take inverse z transform for the following conditions for stable system and causal system and non-causal, this is an anti-causal system. Okay, the system function, then how do you the last pole zero plot. Okay, pole zero plot from z transform, pole zero plot from z transform. So normally the x of z, so the system function is numerator polynomial by denominator polynomial. Okay, a0 plus a1 z minus 1 plus a2 z minus 2 am z per minus m divided by b0 plus b1 z minus 1 plus b2 z minus 2 bn z minus n. So, the poles and zeros are the values of z. So, the numerator polynomials are called poles and zeros. So, the z, poles and zeros are the values of z for which the value of x of z are maybe infinity or 0. X of z may be infinity or 0. Okay. So, this x of z, you can say this is a h of z system function. So, what are the values of x of z? And it has a value of infinity at the poles, infinity at poles, because if it is any at the poles, the system function will be infinite. So, that the poles does not lie in the ROC of x of z. So, this is important note. So, normally the in ROC x of z should have x of z has the finite value, okay. In ROC the x of z has the finite value, but whereas the x of z has the value infinity at poles. The x of z equals to equal to has the value infinity at poles. So, that the poles does not lie in the ROC of the x, y, z. So, the conditions, remember that. So, all these conditions are required to determine whether the given system is stable or unstable system. So, the poles only plays a vital role to determine the stability of the system. So, the poles does not lie in the ROC of x of z, because for ROC condition the x of z has to be a finite value, but x of z will become infinite at poles. Okay. Now, we will take some problem. With this we can the concept of Z transform, how to determine the stability of the system. We will take some examples. The example problems I given. We will solve these three problems one by one and how to determine the stability of the system. I think in this session we can complete the concepts, and the next session we will discuss, will solve the problem for inverse Z transform.